Hi, folks. I'm David Steele, the Director of Innovation at Arcturus. Welcome to the webinar today, and thank you for joining me. Before we get started, I just wanted to cover a couple of quick housekeeping items. First, feel free to send questions along anytime using the chat feature. But what we'll do is we'll reserve some time at the end of the webinar to address them. Secondly, just for your information, we will post a link to download the presentation slides at the end of the webinar as well. So we'll get a copy of those too. Okay, so let's jump in. Today we're going to be talking about Mbarx, which is our secure IoT software solution. So just before we begin that, I thought I would just kick things off quickly by giving you an introduction to the company for those of you who are a little bit less familiar with us. Arcturus has been operating since 2001 and is a privately held Canadian company headquartered here in Toronto in Canada. We started off as an embedded Linux OS board vendor, and we've evolved over the years to add more value in our software. Our focus is mission-critical edge hardware, software, and systems. We provide real-time hardened voice and video communication solutions. We provide edge AI and vision analytics for multiple applications like public safety, retail, and the smart city. And we also provide solutions to secure and connect devices so that they can be managed easily in the field. These align closely with our key technologies, which are SIP Extreme, which is our hardened voice and video communications product, Mbarx, which is our solution for secure connectivity, telemetry, and management. We'll be talking more about this today. And Brink, which is our flagship edge AI and vision product line. Ultimately, with these technologies, what Arcturus brings to the table is really field-proven solutions and a lot of expertise in delivering edge systems and solutions in the marketplace. And speaking about the marketplace, from that standpoint, we tend to focus on three key verticals, although not exclusively: safety, security, and access control for smart buildings and cities, intelligent transportation systems for public transportation networks and fleet vehicles, and smart healthcare systems. And these are primarily in patient care and elder care systems. We have a hardware portfolio. It ranges from microcontroller-based voice and IoT solutions at the low end, all the way up to the low end on the left, all the way up to high-end edge AI and vision systems on the right. And on the right, these support up to 10 64-bit ARM cores, with 23 TOPS of edge AI acceleration. The key thing about our hardware is that it is industrial grade. It's made with extended temperature parts and planned for greater than 10 years of longevity. We actually still sell and manufacture devices that we designed in 2002. In terms of production, we control the process end-to-end. This gives us a lot of flexibility and allows us to control our overall quality. We really do pride ourselves in our quality rates. We have in-field failure rates as low as 0.1% over 10,000 units, which is quite impressive. And just to quickly summarize where we fit and the value we bring, we typically work with OEMs to help them enable products. To do this, we leverage a considerable portfolio of IP and expertise. We've got in-house hardware and software teams. And our products and services are really geared towards two engagement approaches, either a turnkey system solutions engagement or a component level enablement and integration engagement. And we finally have an ecosystem of partners that we work closely with. Our silicon partners at ARM, NVIDIA, VeriSilicon, and Kinara, who support us with getting early access to new technologies. And we have a global presence with Arrow and representation in North America through Electrosource, who also represent ARM, Synopsys, and Siemens as well. So the main purpose of today's webinar is to provide an introduction to Mbarx. Mbarx is our secure IoT ecosystem solution. It provides management, telemetry, and OTA firmware update capability. Mbarx can be used by itself to enable connected products, and it also underpins a lot of our other software stacks by providing the management and telemetry services for them. So for us, Mbarx is very much the backbone of a lot of our systems. As a product line, Mbarx is composed of three things. Number one, secure end-to-end connectivity and management suitable for a broad range of IoT endpoint devices. Number two, tools, including our system manager tool, which is a workflow tool capable of managing local devices or remote sites. And three, edge gateways and stacks that provide secure connectivity, services, and workflow for IoT device networks. Now, we call Mbarx an ecosystem because endpoints, tools, and gateways all work together. This means that they are not reliant on passing data through cloud services, and it does not use insecure methods such as MQTT or COAP. What we've done instead is we've taken the time to develop a solution that uses proper standards-based security using TLS cryptography, certificate-based authentication across the entire system, whether it's a $2 microcontroller or a $2,000 gateway device. Because Mbarx can operate on-prem or in a private cloud, it typically targets industrial and commercial applications. It specifically fits well with applications that have privacy or security considerations that limit the application of public cloud infrastructure, or applications where it's really necessary to tightly control the end-to-end network. And we can look a little bit closer at some of what some of these applications would be. Here are some typical applications where Mbarx fits. In telemetry devices, particularly instruments, remote monitoring, safety or patient care, automation devices, process control, workflow management, manufacture and assembly, and access control in building systems, including entry systems, parking, and HVAC. So how does Mbarx work? Well, this is an overview of the Linux implementation of the Mbarx endpoint stack. The Linux implementation is a superset when we compare it against the RTOS version. However, regardless of RTOS versus Linux, Mbarx supports a full range of capabilities, including device management, configuration, OTA firmware updates, and telemetry data. The system consists of 5 key components. Number one is front-end services. Number two is a back-end daemon that handles requests and responses. Number 3 is a configuration engine. Number 4 is a configuration database. And number 5 is a series of hooks that are built into the OS processes, services, and interfaces and applications that allow for control of their behavior and management of their capabilities. And the way the system works is that it provides a periodic MDNS service discovery broadcast on the network. And what this does is this presents a message with a unique device information. And this service discovery message is sufficient to locate the device on the network and to connect back to one of its available front-end services. And those front-end services can range from a web server for GUI-based configuration using HTTPS, an SNMP agent for configuration using network management stations. We also have a proprietary lightweight IoT protocol called Mbarx ASD. There's file-based provisioning capable of supporting templates. Or there can be any other really required service, such as a language binding or another IoT protocol that can be plugged into that. And each of these can be enabled or disabled depending on the application. So once connected to a service, requests are processed by a backend daemon. If a configuration change is requested, then the daemon sets the object and value in the configuration database and returns the current status to the service. The action of this setting will trigger the database engine to read the database and process any of the changes that have been made. What the engine does is it regenerates the .conf files of the system services and interfaces and applications, as well as hooks into the sysfs and proc file systems to control aspects of the OS. The engine also has access to special database objects that are provided as part of a proprietary API extension on top of the standard Linux U-boot bootloader. And this provides a very high degree of control and flexibility during the boot process, including redefining low-level kernel args and boot parameters. And then finally, as part of Mbarx, there's also integration into a supervisory watchdog subsystem as well. And with Linux, this acts as a service and allows other applications to also register with it. And then you must update that service within a period that they define. And failure to do so would cause the watchdog to either reset that application or terminate that application or reset the board. All right. So having an IoT solution is great, but you need methods to configure it and manage it. On the left, we have screen captures from our Mbarx System Manager tool, and on the right, we have our web UI. The web UI is available on Mbarx Linux platforms, and it provides a local method to configure settings, check logs, upload firmware. System Manager is an application for Windows or Mac that detects devices on the network and presents them in really easy-to-use click-through workflow. And I can give you a quick demo of how System Manager works. The simplest way to do this is using local connectivity in a LAN environment. And in this demo, we're using System Manager to detect devices on a local network. We can see the devices on the network. I can search for specific IoT devices. In this case, these are microcontroller devices. I can just double click on it to connect to it. And then what this will do is it will negotiate a secure TLS connection with the device from System Manager, and then it will pop up a configuration panel presenting all of the device information. So we can see an overview of this particular device. We can see its network settings, including things like its DHCP fallback policy. This is a VoIP device, so it's got VoIP settings and audio settings, control settings, and we'll get into this in a bit more about the remote server connection later, and also admin settings. And so that really shows you how to log into a device and configure it pretty simply, just using System Manager and the device being on the same local LAN. We can also achieve the exact same thing, but in reverse, if that makes sense. In this case, the device is actually calling home to a predefined destination using a remote connection feature. So devices can call home to System Manager, which can run a service to listen for them, or to an Mbarx gateway, and we'll get into gateways in a moment. And the advantage to this method, the advantage to calling home, is that devices can egress their own local network, which makes connectivity much easier, especially if they're behind a NAT firewall. And then once connected, all of the same capabilities are available as it would be with a local LAN connection. And so that I'll demo how this works once we get into some of the gateways, the site controller gateways later on, and I'll show you how the call home feature works in a little bit more detail then. So another key feature of Mbarx is OTA firmware updates, or over-the-air firmware updates. Now, these work by sending a firmware package to the device, which is sent using a secure TLS connection. The firmware package itself is code signed, and that means that its authenticity is verifiable by the device. It also contains compatibility information about the device that it's intended for, to help protect against uploading the firmware to the wrong device, or perhaps uploading the device with incompatible firmware. And finally, the firmware package also contains a checksum to validate that the payload has not been tampered with or has somehow become corrupted during transmission. Now, there are a few differences between the RTOS and Linux implementations of the over-the-air firmware updates. And these are primarily due to the resources and memory that are available and required by each. So in an RTOS system, we can provide a full firmware image payload. In Linux, it's also possible. However, it can be quite large. So what can be beneficial is to actually just target the payload more specifically, and it's going to be much more efficient. And to do this, what we do is we partition the Linux file system, and this allows us to target either a bootloader, the kernel, a base system user land, or application space individually. And that makes it much faster, more efficient, uses less bandwidth, it completes quicker. Another slight difference between RTOS and Linux systems is that due to the smaller size of an RTOS image, it's generally possible to create a fully redundant flash image, which means that there will always be a fully working image on the device at all times. In Linux, this is generally too expensive to create a fully redundant system. So in this case, we provide a rescue image that is sufficient to download and write a new working image. And of course, all of this is supervised by the watchdog system and the U-boot extensions that I mentioned before. So it can be tightly controlled, and any recovery process can be tightly controlled as well. Here's a quick overview of the OTA firmware update workflow using System Manager. The first thing that we provide inside System Manager itself is connectivity to a secure online firmware store. This makes it possible to download firmware from a trusted source and store it locally inside the System Manager repository. And to do this is fairly straightforward. All we need to do is just click on the Get Firmware, and then we'll just log into the System Manager store using our account credentials. And we'll just download the most recent version of the firmware, which is 8.27. And this will download it into the local System Manager repository. Now we can just look for some devices that are running old firmware, and we've found some here that are running R5. We can select the new firmware, and we can start the upgrade process. And this will push a firmware upgrade securely to these 3 devices concurrently over the network. Now, while these are upgrading, what I should mention about the cool part about the System Manager store is that not only did we build the store into a System Manager, but we took the time to build out all of the backend management for it as well. So it supports, as you saw, users, but it also supports administrators and vendors. And this makes it possible for us to provide private stores, or even to create things like a marketplace using System Manager and the System Manager store. So you can see the uploading's almost complete now. And then once that's complete, as it is now, it's going to start flashing the images. I'm just going to go back to the main page here. And those devices will start to reboot, and then it will rebroadcast their information again using that MDNS broadcast. But it's now going to have the updated firmware version as part of that as part of that broadcast, and we can use that to verify that the update is in fact successful. And that's really just how simple the OTA firmware update process is. Now, in the example that I just showed you, this illustrated what we would call a manual push update. But Mbarx also supports auto firmware updates, which makes use of the call home feature that I mentioned earlier, and also the ability to flag specific firmware in the repository. And the cool thing about that is it doesn't have to be the newest firmware. If you need to roll back a firmware version, you can do that. So you can really flag any version you want as the auto upgrade. And it will ensure, using that device broadcast, that it's going to only compatible devices. So in this example, we're using System Manager for the call home server and the firmware upgrade process, but the exact same workflow applies to site controllers or gateways. And we'll get into that later as well. So the first thing we're going to do is import some firmware into our repository. New firmware we can just get from our desktop instead of the store if we want to. Just download and drop that into our local firmware repository. And then what we're going to do is we're going to set the auto upgrade flag on that firmware. And now what we're going to do is we're going to configure the device to call home. And so that involves us connecting to the device, and that's going to pop up the configuration window that we need to set it up. And then we're going to go to the Control tab. And here what we're going to do is we're going to enter the IP address of my System Manager, which you can see in the bottom right corner, which is 192.168.50.121. And we're going to set it to call home to that server once after reboot. So we're going to save this configuration. It's a microcontroller device. It's going to restart. And as it restarts, what it's going to do is it's going to get a DHCP lease, and as soon as it's done that, it's going to reach out to my System Manager version, and it's going to log into it, and it's going to check to see if there's any new firmware updates available at that time. And here we see it's coming in already. We can see the upgrade started already, and that will complete in just a couple of seconds. There we go, and we'll flash it, of course. And then when it reboots, we'll send out that new multicast broadcast with the new firmware update version, or the updated firmware version, pardon me, and we'll be able to confirm that, in fact, it's running the correct firmware. There we go. You can see that that's successful. All right, so I think let's just moving on here. We've covered management and firmware updates, so we should also cover telemetry. That's a key aspect as well. It's pretty straightforward. There are really two components to it. We've already talked about one of them, which is the local MDNS device broadcast. This provides the information that other systems can use to connect to the device or know what firmware it's running or know what its capabilities are. The second part is the protocol called Mbarx ASD. And ASD typically runs on both TCP IP port 107 using TLS security and also on a dedicated UART connection. So on the TCP IP port, you can connect remotely over a network. On a UART connection, you can use a host microcontroller, let's say, to connect to it and host control it that way. ASD is a very simple character-based command protocol that is used for both operation and configuration, and it provides the telemetry interface. And this slide is showing an example of ASD syntax using our virtual control panel application. And in this case, the virtual control panel is connected to one of our UCMK64 VoIP devices. It's a VoIP platform. And in the ASD console, you can see the request response workflow. To start a call, this includes turning on and off various GPIO status outputs, and then ending the call. Also, if you need my cell phone number, it's in here too. so you can't say you can't reach me. But as you can see, it's a fairly simplistic protocol. It's just a character-driven request response protocol, and it's fairly trivial. Before we switch gears and talk about Mbarx gateways, it makes sense just to conclude on the endpoint stacks. From a stack up perspective, this is what the Mbarx stack looks like for Linux, including the tie-ins at the low level to support root of trust and secure file system within the OS, boot arbitration and reboot extensions, all the way up the stack to firmware handling, configuration engine, and watchdog support. And then on top of that, of course, there's the management daemon and services to plug in to provide external connectivity, including MDNS, ASD, HTTPS, file-based provisioning, SNMP, or other language bindings, with whatever, or IoT protocols, whatever needs to be added there. As I mentioned, this is the Linux version. We can compare this to the RTOS version, and we'll notice the stack is pretty similar. The key takeaway here is that it is a different code base, but from the services perspective, it provides identical capability. So you can have a mix of these devices seamlessly on your network, and based on Mbarx, there will be no difference in capability. There are a few less features with the RTOS stack. We obviously don't support a web server in the RTOS stack, but on an MCU, that's unnecessary and frankly doesn't usually make a lot of sense. Mbarx typically fits on MCU devices with less than 100, definitely less than 128 KB of SRAM, including TLS, v1.2 or newer. And we can generally offer fully redundant firmware images, including the OS, in under 1 megabyte of flash. Here's a shopping list of features, also comparing RTOS and Linux implementations of Mbarx. On the top left is a system configuration, which between RTOS and Linux remains pretty much the same. Below is a collection of resiliency and redundancy features, which are used to provide hardening for our products, or Mbarx products. This includes network monitoring, fallback operations, watchdog, and firmware protection. The networking controls are pretty simple on an MCU, but with Linux, they get fairly comprehensive, including hooks into the firewall and routing table. And then the platform trust architecture, and finally, system integration services and tools, which are all pretty similar across both systems. I'm not going to focus too much on this slide. You can deep dive into it once you get the slides if you're interested. Feel free to reach out if you've got any questions. Happy to address those. Okay, let's switch gears and talk about Mbarx gateways. In the previous section, I demonstrated connectivity using System Manager on a local network, and also the remote server connection feature that allows the device to call home. In that case, it was calling home to my System Manager application. But in some cases, it's not desirable to have devices egress their local network at all. And this is where an Mbarx site controller gateway comes in. So Here, what we're going to do is we're going to connect to a public demo site we have set up called iotg.sipgear.net. The machine at iotg.sipgear.net is in fact a site controller that hosts other site controllers. And System Manager is going to log into that, and then we're going to select the site controller we actually want to get to, which is called Minibus Site Controller. We're going to log into it, and once we do, it's going to present a subdomain of all of its IoT devices. And that's what we can see now. So we can see a collection of IoT devices there. And what we can do is just search for one of them. We can just double click on it. And this is the exact same workflow that we would use if it was on a local LAN. So to us, it's completely transparent at this point that we're doing it remotely through a gateway. And this will reach out to that device. It will then create a secure connection with it. And it will bring up that configuration interface that we can use. And we can, again, it's exactly the same interface that we have for a local device. We've got an overview of devices, network. In this case, it's VoIP device again, VoIP, audio, control, and admin settings. And so that can be done using a gateway that keeps all of our IoT devices at that location secure. We only have one way to connect to them, that's through the gateway, and the gateway is secure as well. But as I mentioned, iotg.sipgear.net was a site controller that hosts other site controllers, and that in fact is multi-site connectivity. And this is very useful if you have a network of distributed IoT sites and need to connect and manage each of them. And this can be the case in many environments with distributed locations. A good example is perhaps public transportation, where each station on a network may have its own discrete network of devices. Multi-site connectivity adds a central gateway registrar function that other site controller clients can connect to. The central gateway aggregates and manages the connections to multiple site controller clients. And this makes it possible to have multiple site controllers behind NAT firewalls and still access each of them, and then each of their subnets of IoT devices that are behind each of those site controllers. So this makes connectivity very robust and maintains the security architecture of that type of topology. We have one gateway stack left. That's the Mbarx Operation Controller. It's a pretty useful solution for building workflows. In this case, we're illustrating how we can use it to create a multi-tenant building access controller that doesn't require an app to be natively installed. Instead, it uses web-based workflow and notifications using SMS, push, or VoIP to provide a secure and temporary web link. And then this link provides access back to controls, video, and voice call capability, as well as granting access by controlling the lock striker plate at the door. This same setup can be used for any application where there is human and device workflow involved. A nurse call system in a residential care environment is another very typical example of that. And finally, last but not least, I know this is a bit of an eye chart, but I wanted to illustrate how deeply integrated Mbarx is. All of the small yellow triangles tags in the corner of the blocks in this diagram represent areas where integration is supported by Mbarx. So you can see, and this is a Linux stack, you can see it's fairly comprehensive and well supported. All right, so I think that brings us to the end. I've given you a quick introduction into the Mbarx Secure IoT product line, including Linux and RTOS endpoint support. I've shown you how to securely connect to devices and how that can be extended by using Mbarx site controller gateways. And I've given you a quick introduction to the operations controller for IoT-based workflows using web apps. I want to thank you for joining me today. And what we can do now is transition into the Q&A. I know I saw a couple of questions come up. Let me just gather those together. So the first question is regarding firmware updates using gateways. Does each device need to call home to get a firmware update? So if you're using site controllers, the site controller actually has its own firmware repository built into it. So if you have a network of IoT devices and a site controller managing those IoT devices, you actually upload firmware to the site controller, And then each of those IoT devices at that location will then connect to the site controller separately and download their firmware. So that means that they never actually have to call home outside of their network to get the firmware. And you only ever have to transmit that firmware to the site controller once. So that is typically a much more efficient way of and secure way of doing things. So it reduces attack surface too. I think that answers that question. Another question is, can gateways be used for other Linux services, or do you require another gateway to provide? So right, I think the question is, if you have a site of IoT devices, can a site controller provide things like DHCP, and the answer is yes, it can provide those Linux services like NTP and DHCP and all the things that the IoT devices would rely on to function normally or network from a networking perspective. The site controller also can provide a syslog repository as well. So you can fire all of the syslogs at the site controller, and then you have one central place to download them from and manage them from as well. And the third question is, do we provide any implementation references for ASD? I think the answer is yes and yes and no for that. We do have the virtual control panel, which is built using Qt. I mean, we can provide that as a reference. We typically bundle some support with it just to help you do that. ASD itself is pretty straightforward. You may actually not even need a reference to be able to do that. So those are the questions. I think that sort of brings us to the end of our presentation for today. So again, thank you for joining me, and I look forward to any questions that you have. Please feel free to reach out. Our contact information is here, and we'd be happy to answer those questions for you. Thank you.